Okay, the second issue I want to talk about is what's called the flatness problem. Why was the early universe so flat? Should say a few words about what's meant by flat. First of all, flat does not mean two-dimensional, as I discovered sometimes my audiences think. Flat can mean that, of course, but it's not the meaning I have in mind. Here, by flat, I mean Euclidean, obeying the axioms of Euclidean geometry. According to general relativity, the universe doesn't have to be Euclidean. If you assume that the universe is completely uniform, then you're limited to 3 possible geometries for the universe. Of course, if you don't assume it's uniform, it can be lumpy in all kinds of complicated ways. But the universe certainly appears to be uniform, and now inflation gives us an explanation of that. So if we assume uniformity, just to understand what the options are, there are basically 3 kinds of geometries. There's a closed geometry, which is similar to the surface of a sphere and has the property, like the surface of a sphere, that if you draw a triangle, instead of the 3 angles adding up to 180 degrees, as Euclid tells us they have to, on the surface of a sphere, they add up to something a little bigger than 180 degrees, as I think you can see from the illustration. That's an accurate perspective, by the way. I drew that thing myself. Conversely, one can talk about an open geometry, which is kind of like the surface of a saddle, it's often described as. And in an open geometry, again, as I think you can see from the picture here, the edges, the corners of the triangle get pinched by the curvature, and the sum of the 3 angles adds up to a little less than 180 degrees. And right on the borderline between those 2 possibilities is a flat geometry, the geometry of Euclid, where the 3 angles add up to exactly 180 degrees all the time with no other option. So that's the meaning of the concept of flatness. And the point is that our universe today and the early universe were rather extraordinarily flat. Well, see, first of all, I said the general relativity links the flatness to the mass density of the universe, or maybe more precisely to a relationship between the mass density and the expansion rate. There's something called the critical mass density, which is a number that depends on the expansion rate. It's not a universal constant. And this critical mass density is the density that would make the universe exactly flat. And cosmologists tend to talk about the actual mass density in terms of this ratio called omega. Omega is just the ratio of the actual mass density, whatever it's found to be, divided by this critical mass density, a number that you calculate that depends on the expansion rate. And if omega is 1, the geometry is exactly flat. If omega is bigger than 1, the geometry is closed. And if omega is less than 1, the geometry is open. Now, the fact of physics that gives rise to this flatness problem is that it turns out that the universe is near omega equals 1. And furthermore, omega equals 1 is an unstable equilibrium point. And by unstable equilibrium point, what we mean is that if omega is ever exactly equal to 1, it will stay exactly equal to 1 forever. But if omega is just a little bit off from 1, it will rapidly start to fall in that direction, just like a pencil balancing on its tip. If the pencil is exactly straight up, it will stay straight up forever, at least according to classical physics. We'll pretend quantum theory doesn't apply to this pencil, even if it applies to other pencils. But if this classical pencil is leaning just the tiniest bit in either direction, it will then start to fall in that direction and will fall pretty rapidly once it gets going. So omega equals 1 is just like that. If omega is exactly equal to 1, it will stay 1. But if omega in the early universe were just a tiny bit bigger than 1, it would rapidly start to rise towards infinity. And if omega in the early universe were just a tiny bit less than 1, it would rapidly trail off to 0. And to make that quantitative, we need to consider some particular time, because it depends on what time you're talking about. So let's talk about the universe at 1 second after the Big Bang. I should maybe mention that 1 second is not a crazy time to talk about in terms of conventional cosmology even. One of the big successes, I didn't have a chance to talk about all the features of conventional cosmology, but one of the big successes of conventional cosmology is the accounting it gives for Big Bang nucleosynthesis, how the elements were formed in the Big Bang. And those processes began at about 1 second after the Big Bang. And there's very good agreement between the observed abundances of the light chemical elements in the universe and what you calculate from the Big Bang model. So the Big Bang model is really rather directly tested by nucleosynthesis at timescales as early as about 1 second. So 1 second is a fairly natural time to talk about here. So if we think about the universe at 1 second after the Big Bang, what we find if we put in the detailed calculations connected with this instability is that at 1 second after the Big Bang, the value of omega must have been just what it needs to be, which is 1, to an accuracy of about 15 decimal places, or else we would not be consistent with what we see today. I should add that in conventional cosmology, that's something of a mystery because there's nothing in conventional cosmology that determines the initial value of omega. It's just something you have to put in by hand. So like the previous problem, you can solve it by fiat if you're willing to just assume that the universe started out with omega exactly equal to 1. But if you don't want to assume that and want to try to have some dynamical understanding of how omega got to be so close to 1, then you really cannot do it within the context of conventional cosmology, but inflation offers an answer. So the inflationary solution comes about because inflation changes the whole description of the expansion of the universe. Instead of the expansion slowing down, the expansion is speeded up by inflation, so signs of equations in key places are changed. And in fact, inflation drives omega to 1, and it drives omega to 1 incredibly rapidly. It drives omega to 1 exponentially. So that means that in the context of inflation, omega could start off being almost anything. It could start off being a tenth. It could start off being 10. It could start off being 100th or 100. The further away you start from 1, the more inflation you need to smooth things out. But if you have the amount of inflation that we talked about 100 doublings, that will take you from any reasonable value of omega to a number close enough to 1 to be consistent with what we see. And if you start further, you just need a little bit more inflation. So no matter where you start, inflation will solve the problem as long as you have enough inflation. Now, in fact, because inflation drives omega to 1 exponentially, it means that if you overshoot a little bit, you get a lot closer to 1 than you thought you needed to be. So in other words, the mechanism essentially always overshoots and produces a universe that's not merely as flat as what we observe, but rather a universe that's much flatter, much closer to omega equals 1. So that really gives rise to a prediction of inflation. The prediction is that today, when we measure omega, we should get a number that's, to the accuracy that we can measure it, equal to 1 exactly. So that prediction had some interesting history. Until about 1998, astronomers were not finding omega equals 1. Rather, they were finding omega equals 0.2 or 0.3. Now, I have to admit, thinking back, this always made things a little bit uncomfortable for me when I had dinner with astronomers. They would enjoy pointing out to me that although inflation is a beautiful theory, it doesn't seem to correspond to reality because it predicts omega should be 1, and we can see obviously that it's not. However, the story ends more happily than that. The latest observation of omega, which comes from the Planck satellite combined with some other data, is that omega is equal to 1.0010 plus or minus 0.0065. Or to simplify that statement, omega is equal to 1 to an accuracy of about 0.5%, the accuracy that we know it. So everything is now completely consistent with omega equals 1, which is gorgeous. Now I enjoy having dinner with astronomers. And the new ingredient is what's called dark energy, which probably you've heard about in other contexts. The point is that 1998 marks the year in which astronomers discovered that the expansion of the universe today is not slowing down under the influence of ordinary gravity, but rather today the universe is actually accelerating. And that means that today the universe is apparently, if general relativity is the right theory, filled with some material with a negative pressure, just like the negative pressure that we talked about driving inflation in the early universe. So it's again repulsive gravity, it's again negative pressure, it's probably not in any way the same substance. There's no reason why it should be, although there are some theories that do relate them. So apparently for the last 5 billion years or so, the universe has been dominated by this dark energy and has therefore been accelerating. And the beauty for the present discussion is that when you add in the energy of the dark energy to everything else that we know, you bring the total up from about 0.2 or 0.3 up to 1, to a very high degree of accuracy, about 0.5%.